Welcome to this primer on graphs. In this lecture, we look at the principle of double counting, and this will rely on the notion of bipartite graphs. So let us recall, what is a bipartite graph? A bipartite graph is a graph G with vertex set V and E, and for convenience, you may assume that V is a finite set, but it doesn't matter. So we say G is bipartite if one can partition the set P into two non-empty parts, such that whenever you pick an edge from the set E, of course, you find that one endpoint of the edge is in A and the other endpoint is in B. So if there exists such a partition, we declare that the graph is bipartite. Okay. What is a bipartition of a bipartite graph? Bipartition of a bipartite graph. So given a bipartite graph, G, let's say, a bipartition of G is a partition of the vertex set into two parts. So if this is the vertex set, then a bipartition of the bipartite graph is a partition of the vertex set into two parts, such that any edge has one endpoint in A and the other endpoint in B. So basically, a bipartition of a bipartite graph witnesses the bipartiteness of the graph. Okay, so we discussed this in the previous lecture in detail. And now let us move on. So let us start with a puzzle. The puzzle is this. Suppose we have n people in a party. And suppose the ith person shook hands with total number of di people. So you ask the ith person how many people you shook hands with. He says he shook hands with di people. Di could also be 0. And let us assume that he does not shake hands with himself because, we can take that into account also, but let's not complicate things. So then, what is the total number of handshakes? So given two people, how many handshakes happened? What is the total number of two people who shook hands? How many pairs of people shook hands, if you want to call it, phrase it that way. So that number turns out to be this. It's half of the total number of hands shaken as you count. You survey every person. How many hands did you shake? The first person shakes D1 hands up to ... The nth person shakes Dn hands, and you sum all of it and divide by 2. That is the total number of handshakes. So in particular, this is an even number always. And this is not a deep mystery or anything. If you just think about it for 2 minutes, you will get why this is true. But we will develop a general principle, and this will be a consequence of it. Okay. So we will discuss some definitions. Suppose G is a graph, and I say finite graph. By that, I just mean that the vertex set V is finite. So when we say G is a finite graph, we just mean the number of vertices is finite. Okay. And now, given such a graph G, we say that an edge E in the graph G. So when we say edge E in G, we just mean an element of the set capital E. And this is a way to write it. You could just say E lies in capital E, and it's exactly the same thing as saying that. Okay, so we say an edge E is incident to a vertex V if this happens, which is same as saying that V is an endpoint of E. So let's look at this. Look at this graph drawn here. So suppose you have chosen this vertex A, then this edge is incident with the vertex A because an endpoint of this edge is the vertex A, while this edge is not incident with the vertex A. Okay. So that's the definition of incidence. For a vertex V in the graph, the degree of the vertex V is defined as the total number of edges which are incident with it. right? That's the definition of degree. Let me highlight. And this has a notation. So the notation is this. We write deg, deg, deg. We put v in brackets or not. You can also not put brackets. That's fine. And if you want to emphasize which graph you're working with, you can put a subscript. But if there is no confusion, you may drop the subscript. And we have precisely defined what is the degree, but in symbols you can express the same thing as writing this. It's the cardinality of all those edges which have v as an endpoint. So this is another way to express the same thing. So that's the degree of a vertex. Here, what is the degree of A? The degree of A is 2 because it is incident with 2 edges. C also 2, but B has degree 3. This has 1, and so on. Alright. So the neighbor set of a vertex V, is defined as neighbor, and then you emphasize the graph if you like, and V in brackets or not. So this is defined as all those vertices such that this is an edge. So let's talk about this example. This definition, sure it is clear, but maybe an example will help. So suppose this is my vertex A and I want to find its neighbor set. So I just ask which vertices can I reach just by using one edge, right? That's what this says. So B is a neighbor of A, and this vertex, which I haven't labeled somehow, let's label it. Oops, what is going on? Right, it's standing out, but anyway. So A is a neighbor of F, and A is also a neighbor of B. And the neighbor set of A is basically these two things. Okay. Also, maybe I should introduce another terminology here. So if, maybe I'll write it here. So if you and we are neighbors, then we also say that you and we are adjacent. So it's just another useful or frequently used terminology. Adjacent. Okay. All right. So that's the neighbor set, and it's a simple observation that the degree of V is nothing but the cardinality of the neighbor set. That's the degree of V, clearly. Okay, so let's move on. Maybe there are more terminologies I should introduce here, but we will introduce them when we need them. So now the principle of double counting. It's very straightforward. Fix a bipartite graph G, and let us say we have been given a bipartition of the graph. So this is one part of the vertex set, this is another part of the vertex set, and any edge goes only crisscross. So there is no edge within the pink ones, and there is no edge within the blue ones. So I haven't drawn, actual full edge. It's just, it's supposed to indicate that this edge goes and hits somewhere, but I haven't, drawn an actual picture, complete picture, you could say. So I hope you understand what this figure says. These are not hungry edges, they are actual edges, but I haven't just drawn them in full. Okay, now what is the principle of double counting? It just says that you can count the total number of edges here in the graph in two different ways. One way to count it is by surveying the left side, asking how many edges are you incident with, how many are you, basically asking what is the degree of this person, this person, this person, and so on, and adding all of them. Or you could survey from the right hand side and you will get the same answer. So the principle of double counting says that summation degree x in the left side is equal to summation degree y from the right side, right? So this red corresponds to that and blue corresponds to this. That is the principle of double counting. If you really want to prove it, then you can use well-ordering principle, or equivalently the principle of mathematical induction. If you just delete one vertex, you get a smaller vertex set, and you can apply induction and whatnot. So if you really want a formal proof, I leave that to you, but this should be self-evident, this fact. All right, so now let's move on. Handshake lemma. So suppose we have a finite graph G, vertex set is V, edge set is E. Then the handshake lemma says that the total number of edges in the graph G is given by this formula, and this solves our puzzle that we introduced. In fact, this is precisely the puzzle that we introduced. Basically, if you have n people, you just think of each person as a vertex, and you join an edge between two people if they shook hands. And then the number of people that this guy shook hands with is the degree of this vertex, and the total number of hands shook is the total number of edges in this graph, and this formula immediately establishes what we wrote. So this is what we want to establish, and here is how we do it. So we will develop a new graph. We were given a graph. This was not bipartite or anything. This was just a graph. What we will do is we will develop a new graph. So on the left side, we will put all the vertices of the graph G. So let's say, just for convenience, the vertex set is V1 up to Vn. Okay, so this is, let's say, this is V1, this is V2, this is V3 up to Vn. Okay, and on the right side, this is all the edges. Okay, so let's say the edge set is E1 up to EM. So let's label them also E1, E2, E3. Okay. So this is just the vertex set of our new graph. So the vertex set of our new graph, we will denote like this, is V, and we make the symbol. This just means the disjoint union, which means that, I mean, it is the union. There is no difference between that, because V and E are disjoint sets. So it is the usual union, and when you have two sets which are disjoint and you're taking the union, it is customary to put this symbol rather than just the simple U. So that's all. So the vertex set of our new graph that we will define, we haven't defined the graph yet because we have to prescribe what are the edges in the graph, but the vertex set will be all the vertices and all the edges of the given graph. Okay, now what are the edges? How do we define the edges? So this is defined as, this is fancy V, this is fancy E. So fancy E is defined as x comma E, where x is in the vertex set of the original graph, E is in the edge set of the original graph, such that x is incident with E, or rather E is incident with x, which is same as saying x lies in E, but I write more colloquial. I like using this terminology rather than just saying x is in E. Okay, so this is our edge set. So you basically, what we are doing is you pick a vertex, you pick a vertex, V1 let's say, and ask what are the edges in the graph, in the original graph, which V1 is incident with, and just join it with those in this new graph. Similarly, you ask V2, what are the edges which are incident with it? And you join it with those. Maybe this has no edge incident with it, meaning it is an alone, hungry, lonely vertex in your original graph, in which case this will not be emanating any edges, meaning its degree in this new graph will be 0. Okay. So that's our definition of our new graph, which we will denote by fancy G. So we have a new graph developed out of the old graph, and it captures exactly the same data as the old graph, but in a kind of a different way. So one thing to note is that the degree of any v, so if you take little v in v, now this is an element of the vertex set of the original graph, but this is also an element of the vertex set of the new graph, because after all, this is a subset of that. So the observation that we want to make is that the degree of v in the old graph is same as the degree of v in our new graph. This is a very simple observation. What is the degree of v1, let's say? You're asking how many edges v1 is incident with, and then drawing the same number of edges as many edges are there which are incident with it. That is precisely the definition of the degree of v1 in the original graph. How many edges v1 is incident with? So this is a very simple observation. Okay, what about the degree of any edge in this new graph? So if E is in the set capital E, then what is the degree of E in our new fancy graph, fancy G? This is 2. Because if you have an edge, let's say E1, what is it throwing edges to? It is throwing edges to, or rather it is incident with which vertices in this new graph? Those vertices which were endpoints of this guy in the original graph. But every edge in the original graph has exactly 2 endpoints. Therefore, the degree of this guy is 2. And hence, this picture is much better or more accurate if I delete these extra edges that we had. So this is a more accurate picture of the graph fancy G. Alright, and now apply the principle of double counting to this graph, to this fancy graph. So if you do that, from the counting from the left side, what do we count? We count summation, all the vertices, degrees in the fancy graph, but we showed those are the same as in the old graph. And from the right side, if we count, I will not write y, it's all the edges in the old graph. So this will of course run over all the points in capital E. And what is the degree of any point in this fancy graph of any point on the right hand side? It is 2, as we argued. So this immediately leads to your desired conclusion, because this gives you 1/2. Okay, so alright, so what is the right hand side? This is equal to twice of cardinality of E. That's what that is, and if you just divide by 2 on both sides, you get that result. So that is called the handshake lemma. It has a name, and we see why this is called the handshake lemma, because of the puzzle we introduced. Okay, so this is it for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.